Greetings, everybody. So, what you see here is a question somebody sent me. And rather than just answer their question directly to them, I thought it deserved a video. And so that's what you're looking at right now. Okay. So, the question was to evaluate this definite integral by using integration by parts. It's a definite integral because I have bounds of integration. Okay. So, I'll divide doing that into two parts. Okay. So, part one and part two. Part one, I'll just evaluate the definite integral, meaning I'll just look for the antiderivative of that function that we start with, 3 times sine inverse 3y. Okay. The reason I'll do it that way, the reason I'll do this part separately and intentionally is because to solve this sort of definite integral, what we end up doing is use the fundamental theorem of calculus, which involves us knowing the antiderivative of that function that we started with. Okay, so let's make this. Let's make part one just find that antiderivative. Just evaluate what we'll call the definite integral. Okay, so it did say as a hint here that we would use integration by parts. All right, and that is the way to go on this one. Okay, so integration by parts will work like this. I'll see that this original thing I'm given has two functions. One will be f of y, and the other one will be g prime of y. And I'll have to decide which one is which. Okay, and there's a strategy for deciding. I've talked about the strategy in other videos I made and in other information I put on Canvas, but what I'm going to say now is here's what we'll do. Okay, what will work for this one is if we let f of y be the inverse sine function, sine inverse of 3y specifically, and we'll let g prime be 3. Okay, there's two functions there. One of them I can say is 3. Okay, it's a constant function, but it's still a function, 3. And the other one is this inverse trig function. Okay, so for this to work with integration by parts, the choice I need to make is that f of y is sine inverse 3y and g prime of y is 3. So I choose those. That's the way that it works. Here's what integration by parts looks like. We see the original integral as being f times g prime. I have to decide which of those is f and which is g prime. And then once I make that decision and make my choice, I figure out f prime and g from those choices, okay? So now, all right, if I made the choice that f of y was sine inverse 3y, what's f prime? Well, in concept, that's just the derivative. F prime is whatever the derivative of sine inverse of 3y is supposed to be. Okay. Now, all right, before I tell you about that, you'll see that in this problem, I think you'll discover that you really have to know calculus 1. Okay. I would say to do a lot of calculus 2 in general, you have to be really good at calculus 1. You can't fumble around with basic rules you learn in calculus 1. And so here's one of them. If I make this choice that f of y is sine inverse, then I have to find f prime as a consequence to work the rest of the problem. Then I got to know how you find the derivative of an inverse trig function. Okay, specifically inverse sine function. Here's how it works this time. So the general rule for the derivative of sine inverse of u, where u is some more complicated function. Okay, so sine inverse of u could be 3y, for example. All right. So the derivative of sine inverse of u, whatever the u is 1 over root 1 minus u squared times the derivative of u, whatever that is. So this is how the rule might appear formally in a textbook, okay? So, all right. Now, in my case, I want the derivative of sine inverse of 3y. That u component is 3y. So it'll be 1 over root 1 minus all of 3y squared, which is 9y squared. And then this part will be the derivative of 3y, whatever that is. In this case, that's just 3. So there's your derivative of sine inverse 3y using the rule that you would learn when you learn how to find the derivatives of inverse trig functions, okay? All right, now, so there it is. I'll put that together. It's a 3 over root 1 minus 9y squared. Okay, now what about g of y? I decided on g prime. What does that make g? Well, by definition, if G prime's the derivative of G, right? So that means G is the antiderivative of G prime. So G of y, whatever that is supposed to be, is the antiderivative of 3, which is 3y. Isn't that correct? If you took the derivative of 3y, would you get 3? Yes, you would, and so that's it. All right. So there, now that's everything I need for integration by parts. So remember, the integration parts looks like this. You're given some original integral. It's a product of two functions, f and g prime. You decide which is f, which is g prime. Here's how the decision should work this time. Okay. Then you find f prime and g, and then they all go in this right-hand side of the equation. Okay. All right, now I'll show you that next, but hold on a second. You may see integration by parts written like this, depending on where you look, okay? I got this out of the textbook that's linked with my math lab. It's the same thing. I know it looks different, but it says UDV. That means you'll see two things there. One of them is some function, the other is a derivative. So the U is like what I'm saying is F, and the dV is like what I'm saying is G prime. Okay, but it's identical besides the symbols. It works exactly the same way. All right, so let's see what I found. Okay, so here's your answer. The antiderivative of 3 sine inverse 3y is f times g. Well, according to my choices and what I figured out as a consequence of those choices, that's going to be 3y times sine inverse 3y minus the antiderivative of f prime times g. So that's going to be f prime times g. That's going to be 3y times 3 over root 1 minus 9y squared. So that's how I get this part, okay? All right, so there. Now, I can give you a final answer here if I can tell you what this is. If I know what the antiderivative of 9y over root 1 minus 9y squared. That's the bottleneck at this point, is that, okay, I understood I need to use integration by parts. I chose the functions that are involved. I worked out the rest of it. I put everything in, and now I arrive at this, all by the formula. But I still have to know what this is to complete it, okay? Because unless I've answered that, unless I've found this last indefinite integral, then I'm stuck. I haven't gotten anywhere, okay? So we need to figure out how to solve that. And I think this is where you need to be pretty good with Calculus 1. Sure, you need to know your rules for derivatives, either know them or be able to look them up and understand how to use them. But also, like, what would you do here? If this is the bottleneck, if this is what you have to do to get any further, then what do you do to address that? So this integral all by itself, which is where we're at this moment, that's the kind of thing that you do by use substitution, which is an entire topic all by itself from Calculus 1. Okay? Now, like, I wouldn't show you this as if you'd never seen a use substitution problem. What I have here is, given that maybe it's not fresh on your mind, but you've seen it before, okay? So to solve this by use substitution, the substitution go like this. U would be 1 minus 9y squared. As a consequence, du is the derivative of that, negative 18y dy. But I have to make this such that it can be substituted up there, because it is substitution, all right? I don't see a negative 18y up there. If I mix things together, I see y times dy, but I don't see negative 18y times dy. So I can divide to negative 18, and it says, okay, you can substitute u here for 1 minus 9y squared, and in place of y dy, given that I'm going to take this constant of 9 out, because it doesn't do me any good to leave it in there, then I can substitute negative du over 18, okay? And if I make those substitutions, this integral that seems fairly complicated becomes one like this. It basically becomes the form u to the n du, a very easy basic form of integration. This substitution, done the way that I have it right there, turns it into something much simpler. That's why we often would use substitution, because it takes an integral that is too complicated to handle how it is and turns it into one that's a more basic form. Okay, so I made the substitution after rearranging things a little bit, after removing this constant. And I get like this, okay, where'd that negative du over 18 come from? Well, that came from substituting out y dy. So that negative d over 18, that's a factor there, a constant of 1 over 18 negative. So I can remove that, and I'm getting a negative 9 over 18 if I do that. I'm left with this. This is, like I said, a basic form of integration. There's the antiderivative. Combine the constants and resubstitute for u, and I get this. So look what we did. We did integration by parts. We got here, then we got stuck there. That was u substitution, which we worked. Okay, now we have that, and now we'll put that back in. All right, see how the arrows go? So this is like kind of a footnote to the whole problem right there. All right, so yes, I got here. I realized that I had to solve that all by itself, use substitution. I did that. Now I put my answer back. Why did it become plus? Let's see, that was subtract, right? Subtract the result of this integral, which was negative. So that's why it became positive. All right, so this right here, with our constant of integration added, that's the antiderivative of that original function, 3 sine inverse 3y. Okay, so why would that be important? Well, because to solve in a definite integral, right? The definite integral from 0 to 1/3 of 3 sine inverse 3y dy, the fundamental theorem of calculus says that you can, any antiderivative of this original function will work. If you take any antiderivative of that original function and you put in the upper bound of integration and then you put in the lower bound of integration and you subtract, then that's how you can solve the definite integral. So I found the general antiderivative. The plus c makes it general. But since the fundamental theorem says I can use any antiderivative, we never use the plus c when we do this in practice, okay? Because it offers us no help. So just drop the c. The antiderivative that you'll use is 3y sine inverse 3y plus root 1 minus 9y squared. Now, if I do that, right, I found that antiderivative right there. If I substitute it like so with the fundamental theorem, put in 1/3 into it, you'll get this. Put in 0 into it, you'll get that. With just a very few calculations, you'll get what you want. So the only thing I have to calculate, I think, is what is this sine inverse of 1. Sine inverse of 1 is the angle that has a sine of 1, and that's pi over 2, or 90 degrees. We'll go ahead and leave it in radians. So sine inverse of 1 is pi over 2. So what you get, working all this out, is pi over 2 minus 1. I noticed that that isn't the answer that my math lab seems to want. I got pi over 2 minus 1. It gives me pi minus 2 over 2, but that's no problem. It would just be a matter of adding those fractions together. Pi over 2 minus 1 is pi over 2 minus 2 over 2 if you want to add fractions with a common denominator, and that's pi minus 2 over 2, and then we're done. We got that answer on my math lab. Okay, so I hope you see some themes with this one. I've posted lots of videos of other integration by parts problems. This one has a lot in common with those insofar as it's integration by parts. But you also see that as you do a lot of this stuff in Calculus 2, you'll have to know a lot of things from Calculus 1, okay? You might find as you do this that there are some things that you need to review, and that's okay as long as your attention is drawn to that, and as long as you can make time to review them and ask questions as necessary, then I think you can get a hold of all the information that you need.